The broadcast is now starting. All attendees are in listen-only mode.
Welcome everyone to this webinar on the safety law. The safety law, as you may know by now, because this is the third time that we meet. So thank you so much for joining us. It is the lessons learned publication of the IChemE Safety Centre. It is published every 3 months and it covers different topics, describing 2 case studies in general, and then a short description. After a short description, there are key learning points from each of the studies. The second part of the safety law, which is the second page of the document, because it is a 2-page document that we are talking about, so a very brief, concise one, tackles all tips, recommendations to managers, supervisors, process safety engineers, and operators. What can they do about in order to avoid that such accidents occur in the future? So far, we have published 9 of these safety laws, and the 10th one is actually on alarm management, is going to be published soon, by June, early June, so to speak. So far, we have covered startup accidents in the first safety law, and we covered maintenance on atmospheric storage tanks on the second safety law webinar. You can get access for free, obviously, for all these webinars. I would like to stress that. And they are uploaded on different forums, on LinkedIn, on the YouTube channel by the IChemE Safety Centre. You will get the information at the end of the presentation. Last time, it was really interesting, and I was really happy about it, that I asked you to please use the chat box and give some ideas, tips, recommendations, share your experience and what you can do about in your practice, what you are practicing in your operation, in order to let others know about the same, because we are here obviously to share knowledge, share those key lessons, and maybe this is the way how we can help each other and motivate each other to do it better. What I am able to is present the law, and since it is a wide range of areas and topics that I'm covering from law to law, obviously I cannot an expert. I cannot be, and I don't want to be an expert in everything, but I would like to provide you the information that I have found through research activities. So, for instance, the 2 case studies that I present in the beginning, those key learning points are related strictly to those case studies. Meanwhile, the second page that addresses the What Can I Do session, actually those recommendations are coming from different sources of information, from different publications, so based on research activities that I'm doing. And today we are talking about flare systems. Luckily, we have a really extensive literature provided on the internet about flare systems, and you can have access to many freely available, publicly available scientific journals, practices, standards, regulations, guidance documents on how to operate flare systems, what are the hazards of flare systems, and actually when we don't have lockdown, normally IChemE runs a training course on flare systems. So before we start, just a brief introduction who were not here before. This is me, this is Susanna Gyenes, and I am the deputy to the director of the IChemE Safety Centre. In my previous jobs, I used to be a Seveso site or Coma site, depending on which country we are from, inspector for almost 10 years, and also I conducted research activities in the European Commission's Joint Research Centre. And my main area was learning from major accidents and I was the administrator of the European Major Accident Reporting System, so-called EMARS, where we have actually more than 1,000 accident reports from the European Union countries. Those are actually based on the regulations, are obliged to report their major accidents, given a set of criteria laid down in the Seveso directive. And also it is open to OECD countries to report their accidents, which we have from Canada, from Australia, from the United States, and different parts of the world. I think even we have Japan reported to it. And then also there is the opportunity for UNECE countries to report. Now, coming back to our publication by the IChemE Safety Centre, the law is free to download. So I highly recommend it to you that if you are interested, I will give you the link in the end of the presentation that you can download the law, as well as you can listen to the podcast where with the director of the IChemE Safety Centre, Trish Kerin, we talk about the law. Now, flare systems, and I'm pretty sure that those of you who already joined this webinar, you have an extensive knowledge, but just a reminder, flare systems in oil and gas plants play a critical role in their safe operation. They are generally used to handle materials vented during normal operations, startup, and emergency conditions. The flare collects a range of gaseous emissions and pipes them to a flare stack where the harmful gases are burned, and then the exhaust is safely discharged to the atmosphere. As a matter of fact, the flare is the last line of defense in the safe emergency release system in a refinery or a chemical plant. As I mentioned before, it is used to dispose of purged and wasted products from refineries, unrecoverable gases emerging with oil from oil wells, vented gases from blast furnaces, unused gases from coke ovens, and gaseous water from chemical industries. If you have additional examples, please feel free to enter your additional thoughts in the chat box. I will come back to those chat box related texts during the presentation or at the end of the presentation, as well as to your questions. The hazards associated with flare systems can be a wide range, coming from embrittlement through corrosion due to low temperature causing failure of the pipe collection system within the flare system, explosion within the flare system, heat radiation, or, for instance, liquid carryover. And in fact, I just looked at statistics, and it shows that approximately 50% of failures are caused by corrosion. And I just want to highlight that corrosion is one of the underlying causes of, for instance, aging of assets, which I will be covering in the next law. I have a question here, and I would like your help with this. Somebody asked, does the hazards applying to flare systems also apply to thermal oxidizers? If you have the answer, please enter into the chat box to our colleague. And I'm going back to the presentation. Let's see now our first case. The first case occurred at an oil refinery. A series of severe electrical storms caused refinery-wide unit shutdowns, including the fluidized catalytic cracking unit, known as FCCU. The crude distillation unit was shut down as a result of a fire which had been started by a lightning strike. A process upset in the FCCU's gas recovery section ultimately led to a high liquid level in the flare drum and several shutdowns of the wet gas compressor, together with other process anomalies. Now, as a result of the wet gas compressor shutdown, there was a large vapor load on the FCC flare system, which eventually led to a high liquid level in the flare drum. When the hydrocarbon liquid overflowed into the outlet line of this drum, the line ruptured due to mechanical shock, and approximately 20 tons of flammable hydrocarbons escaped. And this mixture found a source of ignition approximately 110 meters from the flare drum and subsequently exploded. And that explosion caused a major hydrocarbon fire at the flare drum outlet itself, and, as you can imagine, a number of secondary fires. What we can learn about this case. This is the point where I always explain that all the investigation reports have many, many recommendations, obviously, because there are certain elements and certain underlying causes, contributing factors are revealed by investigations. So you can have such a massive book type of investigation report. You can have a small report depending on your investigation, and then they can address many, many aspects of the incident. Even though we have a lot of learning points from this case, because it is not only the flare system, the design of the flare system that I will talk about in a couple of seconds now, but also a NATEC event, so a natural disaster caused or triggered technological events that you can address here. But I would like to stress that what I am focusing in these laws is always the recommendations or the learning points related to the particular topic. So even if we have so many recommendations and so many learning points, I will see only this that is related to this particular case. Coming back to our case, the explosion apparently was caused by flammable hydrocarbon liquid being continuously pumped into a process vessel that, due to a valve malfunction, had its outlet closed. The only means of escape of this hydrocarbon, once the vessel was full, was through the pressure relief system and then to the flare line. The flare system was not designed to cope with this excursion from normal operation, and due to liquid breakthrough at the FCCU flare knockout drum, a failure occurred in the outlet pipe. The investigation revealed that internal acidic corrosion also contributed to the pipeline rupture. Apparently, the company didn't inspect the weakest points of the pipeline, which were exposed to corrosion. You can have a lot of information about corrosion, corrosion under insulation, chemical corrosion, many different types of corrosions from different reports. But it is interesting to see that this is also the case. As I mentioned, statistics show that 50% of failure of flare systems actually are related to corrosion. And in the meantime, I see that you are really kind and give your answers in the chat box or question box. You can use whichever you want and whichever you see, okay? Maybe it is just a question box. I will come back to those later. The second case that I would like to tell you about may not be related completely to the flare failure, but it is related to the system. And that's why I took this case. It occurred in a crude oil distillation unit. In a crude oil distillation unit, tests showed that the flare system valve was not providing effective isolation and would require eventual removal for overhaul at a scheduled shutdown of the flare. Now, a cold work permit to work was issued 2 days prior to the incident. Alternate flange bolts were removed and the other bolts lubricated, as it was the standard practice to save time. Sufficient bolts remained at all times to retain the flange seals. There was, at the time, no need to verify line conditions. 2 contractors wearing breathing apparatus completed the work. When almost all the bolts were undone, liquid leaked from the gap between the flanges, and gas escaped from the top of the joint. The men stopped working, came down to ground level, and sought advice. The supervisor checked the platform and saw gas issuing from the top and liquid leaking from the bottom of the flange. He concluded that neither was under pressure and that the quantity of liquid was small. Without any further tests, assured the contractor workers that it was safe for work to continue. The fitters remained concerned, thus asked and received spark-proof tools to continue their work. Liquid continued to leak as more bolts were removed. And then, as the last bolt was undone and the crane took the strain and started to lift the valve, the spacer suddenly sprang upwards. A large quantity of liquid was released, a flammable vapor cloud formed and ignited by the nearby compressor. The 2 workers died in the incident. Before I go to the learning points, I'm sorry I always interrupt this session, but more thoughts are coming. I will address such case in the permit to work system safety law. So if you want to hear more about that, then please come to that webinar as well. And I will have a law webinar on flanges and joints. So that might be your interest as well. The key learning points, and you can add more if you have more on that. A tower scaffold with a working platform and access ladder had been erected for work on the valve, but due to access restrictions, it was necessary to climb over or under it. This seriously limited the route of escape. Work on the valve should not started prior to verification of the isolation and shouldn't have continued after the first leak occurred until all doubt about the safety of the situation had been resolved. The absence of the spark arrestor on the compressor was not known until after the incident. And actually that was the ignition source in this case. After presenting these 2 cases, we come back and we come to the point where we discuss a key part of the safety law where we want to understand what you can do at your facility based on your role. So what are the key learning points? These are associated with the 6 elements, of the ISC framework, which are the followings: systems and procedures, engineering and design, assurance, knowledge and competence, human factors, and culture. And all are underpinned by leadership. Because the IChemE Safety Centre, we believe that leadership across these 6 key functional elements is vital to achieve good process safety outcomes. So, as you can see here, there are colored dots associated with each element. In the PDF document of the safety law, in the What Can I Do session, those elements are linked to the recommendations, to the tips. So you can check which are the elements that are linked and which are related to the particular recommendation. I highly suggest you to download the PDF version because I haven't indicated the dots in this in the webinar, but you can see it in the PDF document. Coming back to this safety law on the flare system, what can I do as a manager? And you can have more to this list. I would like to highlight aspects which may give you the idea and more thoughts to add your examples and your practice. So, ensure that all relevant standards and codes are followed, including how to mitigate liquid breakthrough. Identify the hazards associated with flare systems and check that safeguards are available and adequate. Make sure that maintenance activities are considered in sufficient detail during PHA and HAZOP reviews. Ensure sources of flare blockage are understood. Contingent plans are developed to address possible obstructions in the flare systems. It is a major hazard to flare systems, by the way, so I wanted to highlight that. Ensure that rigorous risk assessments have been undertaken prior to jobs of such a high magnitude and potential hazard, such as maintenance of a flare system. Make sure that maintenance supervisors have the competency to undertake responsibilities and to perform their activities to a recognized standard on a sustained basis. This is what we saw in the second case, where unfortunately the supervisor made a decision that he allowed the work to continue. But it is not a very regular case. I believe so. But still, it is important. Competency is really important. The IChemE Safety Centre published guidance document, which is a practical guidance document with the IChemE safety member companies on competency and how to reach different levels of competency. And it is also freely available on our website within and also together with a supplementary guidance document, which actually addresses how to reach different types of level of competency in practice. Finally, as management, develop detailed procedures for drainage and isolation of lines and opening of pipelines and flanges and ensure that these are followed. Now, these are for the managers in terms of flare systems. Now, let's look at the recommendations for process safety engineers and supervisors. You can add to this list, obviously, as I mentioned earlier, from your practice, from different sources of information. So, for instance, in case of ammonia production facilities, because we are not only talking about oil refineries and different chemical plants, but in terms of ammonia production facilities, ensure flare systems containing ammonia are segregated from the flare systems containing carbon dioxide, as the mixing can cause plugging problems. In addition to ensuring the permit to work system is used, job-specific task risk assessment are needed for higher risk activities. Ensure that deviations from these systems are risk assessed prior to execution. As a supervisor, supervise and control the work. Check that the procedures are always followed. Talk through the hazards and maintenance procedure with the workforce before issuing a permit to work. Ensure flare line isolation valves incorporate valve position indicators. Process isolation and preparation plan should be clearly documented and checked. Positive isolation and drainage checks must be performed prior to work commencing. What else you can do as a supervisor or a process safety engineer in this case? Make sure that adequate means of escape in case of an emergency are provided, especially at elevated working platform. A single egress point is not sufficient in an emergency. So, interestingly, this particular recommendation is coming from not only one case. Actually, when I analyzed the permit to work system related accidents, I've come across many of those where the means of escape were not provided, or just there was one single egress point, and it is just a kind reminder that is not sufficient in an emergency. Prepare an emergency response plan to enable workers to escape or act upon in case of emergency. This seems trivial, but it's again coming from different cases. So it is a bad practice that sometimes there is no emergency plan prepared. Check that all personal protection equipment that is required for the work is present and fit for purpose. Workers should wear fireproof suits until the lines are proved safe. Check for the presence of residual flammable gas, avoiding a flammable atmosphere. Use of nitrogen to purge lines should be considered, but used with caution. It could cause pyrophoric deposits to dry out, and therefore increasing their flammability. Working areas should be drenched in water until open pipes have been blanked or spaded. In case of any abnormal situation, meaning leak or, for instance, rupture, work must be stopped immediately and shouldn't start again until a thorough inspection if it is safe for work to continue. And coming now to the part where we discuss what as an operator can do. Before going to that, I always highlight this. Sorry for the repetition, but for those who haven't been here for in the first two webinars, I would like to highlight that despite the fact that these recommendations are specifically addressed to different roles, it doesn't mean that other roles should not read those recommendations. What do I mean by that? So, for instance, if I am a supervisor, I can still read all the recommendations or tips that are related to operators and that are related to managers so that I can get a clear picture. But I have ownership very, very clearly on my part and in my role that are associated with my role. So as an operator, even if you have like only these 4 points, it doesn't mean that they shouldn't know anything about what the supervisors have to pay attention to in this case, or in any case for that matter. I hope it was clear. Sometimes I just whizzing around, but everybody should have a basic understanding of what should be done and how. So as an operator, make sure that no flammable gas or vapor is left inside the system prior to cold or hot work activities. In case of an emergency situation, ask the supervisor for further advice on whether the work can be completed or additional checks are necessary. Ensure that relevant personal protection equipment is available, such as breathing apparatus. When completing process isolation and draining, a positive check should be conducted to prove them. So again, this was not a complete list of recommendation, but at least gave you some ideas what as an operator can do about relating to flare system safety and when you conduct your work. More information and the source of information that you can download the PDF version of the safety law. You can see here that we have the safety law available in English and in Spanish languages. And there is also an MP3 format of the law as in form of a podcast that you can download. And please feel free to distribute all versions. And also, I would like to encourage you to visit our website. Here you can see the www.IChemE for other publications that the IChemE Safety Centre, all together with the member companies to the IChemE Safety Centre, put together. Because the essence of these guidance documents actually is that these companies put a lot of effort to provide their practice and to share their knowledge and information about how they do actually what they do. And those practical suggestions and examples are written in these guidance documents, which are not large, not long documents, so that they can be implemented easily with conducting a gap analysis. And they are obviously not obligatory, but if you want, you can check your system against those guidance documents, and then maybe you find something interesting. There are guidance documents on, as I mentioned earlier, competency, and there are guidance documents on metrics. And soon, very, very soon, in the next couple of days or so, we are speaking about, it's The new publication on early stage or concept phase projects will be published on our website, so stay tuned. And here you can find us on different forums, media, as I already mentioned, such as the YouTube channel, Facebook, Instagram, LinkedIn. We also publish the next date of the webinar. As I mentioned earlier, the next law will be on aging assets. Now, thanks to you, we have quite a lot of messages and questions. So if you don't mind, I'm coming back to the first question that actually was related to whether the hazards applying to flare systems also apply to thermal oxidizers. Well, some of you mentioned that some hazards are common with thermal oxidizers are not the same as flare. The flare blowdown drums are also supposed to have the auto start of the liquid pumps on high level. Some of you said, this is a very essential feature of the flare system. Thank you so much for that. Somebody asked, I guess it was the first case, was the KO drum undersized? Potentially. I have only the information from the investigation report that it was not designed to tackle. I think it was, most probably it was undersized. Was it lack of inspection or the credible threat not considered in the risk-based inspection, and hence the inspection technique not matched with the credible threat? That's a good question. I have to look it up in the investigation report, and I will come back to you with this question. Oh, can we have pictures? Yes. Well, last time and the first time, I think also that I've been asked about pictures. Or PFDs. Not all of these accident reports are coming with PFDs and pictures. And I don't have any intention to add pictures that are not related to the case. So I'm afraid I won't be able to provide with pictures, or PFDs maybe in case I have. But you have to understand that the law is a 2-page document. And so it addresses the brief description of the incident, highlighting the major key learning points associated with the topic. I was thinking about presenting a typical flare stack and how it actually works, but then I decided not to, because you can get that information from the internet. There is a massive information available. So apologies for not providing that, but that is not the essence of this law. Some of you says that I think one of the biggest concern about flare system hazard is the flame put off and thus discharge of unburned gases, especially toxic ones, into the atmosphere. That is a really, really interesting and good comment. So thank you so much. There is another question. How far was the compressor away from the valve? Very specific question. As I said, I will most probably give you more information from the investigation report, because that is not tackled in the law. And again, another big hazard is liquid hydrocarbon carryover to flare tip, which causes fireball, which has caused a lot of damage in the refineries. The liquid carryover is due to lack of skimming of oil in liquid seal drum. Yes, indeed, in the beginning, actually, I mentioned as a potential hazard of liquid carryover. And thank you so much for highlighting and addressing it. Another problem is vacuum in flare headers due to dumping of condensable media like steam and very hot hydrocarbons, which are condensable. This is a major headache for flare system operators. In one of my experiences, there was a leak in the main flare header. When inspected, it was found that the flare header slope, which should have been toward the knockout drum, was not proper, which led to liquid accumulation at a point which ultimately caused imbalance of the stresses in the pipeline and thus a leak. This clearly indicates the importance of good design aspects. Thank you. That was a really valuable comment. What are the flashback causes in the flare stack? What are the process parameters governing that phenomena? I think that you can get it more precisely from scientific journals and practical guidance documents. Another comment, sizing of flare systems for liquid fluid carryover played a part in case study 1. What is the best practice for sizing for worst case carryover from upstream vessel segments in terms of carryover, time or capacity relative to user? These are really, really good questions and really detailed questions. I try to come back to you by email, okay, if I find the answer. Any guidance on nitrogen purging to prevent flammable pyrophoric forming, but also prevent flammable atmosphere? Well, I have to see if there is an interest in that particular area, because it is really specific and really detailed. And in the lore, I tackle basically bigger areas, wider areas, but nonetheless, I will check if there is any guidance, and I try to find it for you and send it to you by email. All right, there is another specific question related to the first case, which I will be able to answer only from the investigation report. There is consideration of the implementation of high-level trips on flare knockout drums to trip the upstream flow. However, the difficulties with older refineries is then the requirement to trip the upstream units and the complexity of trip functions to know which upstream units to trip. The alternative are high-level alarms reliant on adequate knockout drum residence time to allow an operator to diagnose where the overfill is coming from and manually stop the upstream source. Thank you for that. And need to ensure that the liquid removal from drum is correctly set up. Often find pumps are in manual or valves are closed. Should be verified weekly. Thank you again. Another question about a very specific guidance on what size of segments pipework require emergency relief. Okay. General power failure is the worst case scenario. Yes, that is really relevant here. Yes, for designers. Okay, yes, I will send the answer to those that are interested. So please feel free to send your emails, requests, inquiries to the Safety Centre at IChemE.org email address, and I will try to come back to you. These are very specific questions, and we don't have actually the time to address all of them. Wow. Okay. Thank you so much for all of your questions. I'm afraid I won't be able to address more. And please send your comments and questions by email. Thank you so much for paying attention, and thank you for coming to this lore. And I would like to say goodbye to you and thank you. And I hope to see you again next week when I will address aging. Aging is a really, really interesting phenomenon. Oh, final one. Inspection of flare systems are often ignored because it is a common area that is never shut down. Need to have a robust plan. Thank you for that. So with that comment, I would like to close the session today. And I would like to say goodbye to all of you. Thank you.